然后觉得签到可能要加速了哈。签完赶快往前移动，不要挡住后面的。那个因为我们修课的人非常多，所以那个座位的时候不要中间有空，往中间靠，就你跟隔壁最好不要有空位。后面还有很多同学要进来。下次那个签到单多准备2、3张啊，好吧，这样他可以结签比较快。Okay, so I think it's about the time that we should start. So today it's a great honor to have my good friend and our good friend Albert Kong to deliver this colloquium. And even though I know him in person pretty well, but I still decided to, look at his CV to make sure that I didn't miss any point. So Albert is a distinguished professor from the Institute of Astronomy at National Tsinghua University, and he got his PhD from University of Oxford, and then became a postdoc at Harvard Smithsonian Center for Astrophysics and MIT. And then he returned to Asia. He returned to Asia in 2007, and since then he has been working on research. Or change my position. Yeah. Yeah, he has been working on research to understand the physical nature of cosmic ray sources. Maybe I should switch to the other.
The other line.
Using the multi-frequency or say multi-wavelength approach, that's the thing that he has been promoting over quite some time. And then his main research interests focus on high-energy astrophysics and multi-messenger astronomy. And he won quite a few of awards, and among those, I think one critical one is the Outstanding Research Award by MOST, the Ministry of Science and Technology 科技部 in 2015. And then he was elected as a fellow of the Physical Society of Taiwan 3 years later, 2018. And then since 2017, nearly 5 years ago, he has a chance to join the Japanese underground gravitational wave experiment at the Kagwa. So since then, he puts a lot of effort into that, to make it happen, trying to bring more Taiwanese components into that international collaboration. So let's welcome Albert. Right?
Good afternoon, everyone. Thanks for the introductions. It's always good to read foreign the CV because I don't know why. Maybe we're good friends. Many people thought that I'm from Cambridge.
Not you.
Yeah, not me. I'm from Oxford. So anyway, so today I'm going to give you a very brief introduction, a summary of gravitational wave astrophysics in Taiwan. Okay, really focusing on Taiwan because in the last few years, many Taiwanese scientists are working in the experiment concerned about gravitational wave, and I will give you a very brief introduction of all the experiments and also some results as well. Okay, in particular, in the last few years, the very famous detectors LIGO has been working for a while, and we have some very, very nice results. And I will also give you summarize some key results that we have so far. Okay. So because all of you are physicists, so I assume you know gravitational wave. So I don't need to go through all the introductions. Okay. So this graph probably you are very familiar with, even if you're not working in astronomy, astrophysics, or gravitational wave, you probably see this kind of graph many, many times. Okay, so this is the first detections of gravitational wave. Okay, so so in the following, when you see something like the GW and then some number, this is the naming method. Okay. That we adopt to name a gravitational wave event. So GW stands for gravitational wave, and then of course 150914 for this case. This source was discovered in 2015, okay, September 14th. Okay, so you know when this source was discovered. So this is the really the first gravitational wave, direct observations of a gravitational wave. Okay, so you so at that time, only the LIGO detector operated. I will briefly introduce the LIGO detector. So basically, for LIGO, there are two detectors. Okay, so then they see the signal. Here is the time, and then is the strength of the gravitational wave source. Okay, so you can see that the signal becomes stronger and stronger approach when two black holes merge. So in this case, as I just mentioned, we are looking at the merger of two black holes. So we are looking at the two black holes that are rotating with each other. Okay, and then at the later stage of the merging, then they merge together. Okay, and then to create this strong signal. Okay, so this is the signal that we observe from the detectors. Okay, so basically we use this kind of technique, okay, to measure the gravitational wave. Now, so there are several very important messages from this first discovery. So for many of the people, okay, of course it showed that the gravitational wave is real, because I think by the time when this discovery announced in 2016, probably many of you are just coming to NTU for the first year, okay, or maybe second year. Okay, when you learn gravitational wave or relativity, you have some feeling. Okay, we are now looking at some real event. Okay, so in the past, like in my generations, we can only appreciate the beauty of the mathematics. Okay, and also some wonderful predictions. Okay, for example, the orbital precessions, okay, or the gravitational lensing. Okay, so we can look at all those wonderful predictions and observations, but there's no direct or the real thing in front of us. Okay, but by the time you study general relativity, you already have something, okay, in front of you. This is the real event. So this is of course very important, and of course it is a further confirmations for Einstein's general relativity. Once again, he's right. Okay, so that is good. But there's also something that maybe, especially for many physicists, they may not be pay attention about. That is, this detection also show you that black hole is a real object. Okay, as I mentioned before, for these detections, we are now looking at two black holes. They're rotating with each other. And then at the end, because they're losing the energy by gravitational wave, and at the end, they merge together. Okay, and then we see a strong signal. And of course, from the waveform, okay, we can actually model, okay, know, okay, for example, the mass of the black holes or the mass of the objects. Okay, if it is a very, very massive, then we know that it must be a black hole. Okay, so we at least we know the mass of the objects, the mass ratios, and even if the observation is good enough, we can measure the inclination angle, the spin, okay, in the future as well. Okay, so the most important message, at least for astronomer or astrophysicist, okay, black hole is real. And also, another thing is that black holes can merge together. So which means that the two black holes, or here I want multiple black holes because it is also possible that 3 or 4 black holes, they can combine together. So at least this is the first direct evidence. Okay, black holes are real objects, and then they can merge. Now, if you're not studying astronomy, astrophysics, I here need to give you a very brief introduction. What we mentioned about here, about black holes, is what we call a stellar mass black holes. Okay. These black holes, the mass is roughly speaking about 10 to 100 solar masses. But I will give you, show you later that actually it is the maximum mass of a stellar mass black hole, maybe about 50, 60 solar mass. Okay, there's a mass gap here. But anyway, we are talking about a collapse of massive stars. And then at the end, it becomes a black hole. This is what we call a stellar mass black hole. Now, of course, 2 years ago, 2020, we have discovered not really, we already know the result. Okay, so there are 2 observations. Okay, one of course is the very famous, okay, the black hole shadow image. So we know that, okay, we look at the shadow of a black hole. Okay, so at least we look at the pictures. We have the pictures of a black hole. Of course, pictures show you, basically tell you that it is a real object. Okay, and then the other very important thing about this black holes is, of course, 2 years ago, we have the Nobel Prize in Physics. Half of the prize is given to the discovery of a supermassive black hole at the center, okay, of the Milky Way. So by tracing all the stars orbiting around the center of the Milky Way, we can calculate the mass of this central object. It turns out it's very, very massive. Now, these 2 types of black holes, no matter you are looking at the black hole shadow image or the orbiting around the Milky Way, we are talking about a supermassive black hole, which is at least million solar mass. Okay, so they are usually at the center of a galaxy. So you need to distinguish these 2 types of black holes. Okay, so now we have observation from gravitational wave that show you stellar mass black holes. Okay, and then we have something at the center of the galaxy, supermassive black holes. So for this one, million solar mass at least, and then for the other one, roughly speaking, 10 to 100 solar mass, this scale. So what in the middle? Is there anything several hundred or several thousand solar mass? And then also the other question is that how a supermassive black hole formed in the early universe? Okay, so one idea is that we can just, because we just show that multiple black holes can merge together, then in principle we can just merge many of these stellar mass black holes. We can achieve a supermassive black holes. Okay, but some observation also show that we already know that some of the supermassive black holes are in the very early universe. So if the universe only consists of stellar mass black holes, actually there are not enough time to merge in order to become supermassive black holes. Okay. So some astronomer or astrophysicists propose that maybe in the middle, okay, we have something in the middle, maybe 1,000 or 700 solar mass, and then they merge together, and at the end they form supermassive black holes. This type of black hole we call intermediate mass black holes. So later on in the talk, I will also show you also one of the strong evidence, well not really strong evidence, like real evidence that intermediate mass black hole exists. Okay. Also from gravitational wave observations. So here just to give you an idea in case if you're not an astronomer. Okay, so of course we know that 2017 we have the Nobel Prize in Physics awarded for gravitational wave, and it's not very surprising. Now for this discovery, of course, one of the major experiment is the LIGO detectors. Okay, so basically, for LIGO detector, the principle is just a Michelson experiment. Okay, and then it's just scale it up. Okay, so you can just play around it. I think you may already do this experiment in general physics. Okay, but we just scale up to the arm, the two arms, each of the arm. The distance is about 4 kilometers. Okay, so it's just a huge Michelson experiment. So for the LIGO detector, there are two detectors in America. Okay, one in Hanford and the other in Livingston. So basically, the structures they're more or less the same. Okay, we just look at the locations of the detectors. Okay, so one of them is in the northwest, okay, another in the southeast. So, which means that in principle, if a gravitational wave just come across the Earth, there will be a time delay between these two detectors. Okay, and then from the time delay, we can figure out roughly the directions of the gravitational wave. So we have a very, very rough information about the localizations, the regions that the gravitational wave come from. Okay, so later on, I want to introduce other detectors. By adding more detectors, we can have a better localizations of the event. Okay, so this graph is just to show you the principle of the LIGO detectors or other detectors that I will introduce later. So this is just a scale up Michelson experiment. Okay, but with a very, very long arm length. Okay. So LIGO is in America. Okay, so here is another detector in Europe, in Italy. We call it Virgo. Okay, here I show you two images, but actually it's the same detector, same building. Okay, so Virgo only has one detector in Italy. Okay, so as you can also see that the structure is more or less the same. The arm length, okay, is a little bit shorter, 3 kilometers. Okay. So in the past few years, basically LIGO and Virgo are working together. So they observe the sky simultaneously at the same time. Okay, so that we have better localizations. Okay, so this graph is to show you the schedule of this worldwide gravitational wave detectors. So I already introduced you the LIGO and Virgo. So basically, for each the observations for gravitational wave is like this. We classify, we just divide the observation into different periods. Okay, so for each period, we just start with the O. O stands for just observing one. Okay, so we have O1, O2, O3, and in the future we have O4. Okay, so of course the O1 is the first discovery of gravitational wave. Okay, and then the Virgo joined the observations near the end of O2. Okay, so you can see that just near the end. And then usually in the gravitational wave observations, each observing one, okay, may last for about a year. Okay, and then after the observation, they will just terminate, just stop the observations, okay, and then do an upgrade. Okay, So basically, you expect that the sensitivity will be getting better and better and better. Okay. So for example, if you look at this plot, okay, you can see some number above this bar. So this is actually the represented sensitivity. Okay. So this MPC means megaparsec. If you study astronomy, you may already know that. It's just a unit for distance. Okay. Here, which means that how far we can observe emergent binary stars. So in this case, it's two binary stars merged together. Okay, how far we can observe such an object. So of course, the larger the number, okay, the better the sensitivity. So if you don't know what is neutron star, doesn't matter. Okay, you just check this. The larger the number, the better the sensitivity. So basically, after each observing one, the sensitivity will get better and better because we will do the upgrade. We are actually at the here now, okay, to 2022. But because of all the delay due to the COVID-19, actually the next observing one will start from 2022, which is later this year from December. So we have almost a year of delay for observations. Okay, but anyway, it's also not bad because we can also take more time to upgrade the facility so that we can have a better sensitivity. Okay, so you can see that here O1, and then after half a year we have the O2, and then we have a 1 year break, and then for O3 basically LIGO and Virgo are working together. Okay, so they just observe together. And then later on, in this talk, I will introduce another experiment for Kagura, which is located in Japan. Okay, so Kagura also joined the observing one. Okay, later in 2020. Okay, I will also tell you a little bit more about this experiment later as well. Okay, so we are now just in the middle of the upgrade. Okay, and then hopefully we will start in December. Then all three detectors will work together to observe gravitational wave. Okay, here on the left-hand side, you can see just the plot to show you the number of gravitational wave event. Actually, it's not actually an event, it's an alert, because whenever a detector detects a gravitational wave, okay, if we think that is potentially is a real event, okay, then we will send an alert to all the astronomers, okay, so that other astronomers can follow that up with other facilities. Okay, so this is just an alert, not necessarily a real event, but anyway, you can see the trend. So for example, in O1, we can only have a handful of candidates for gravitational wave, okay, because it's understandable the sensitivity is not good enough, and we only have just one LIGO detectors. And then for O2, with better sensitivity, we're getting a little bit more. But you can see that in O3, there's a sharp rise in the distributions. Okay, so in O3 and also in the future in O4, we will also divide it into the observing one into A and B. Okay, so in between A and B, there will be about a month to maintain the detectors. For example, to do some slight modifications or improvement. Okay. There will be just a 1 month break between the A and B sessions. Okay, so you can see that in the O3, there's a significant increase in the gravitational wave event alert. Okay. Now, on the right-hand side, it's just an interesting project just to show you to give you some idea, okay, about all the events that we detect by these detectors. Okay, LIGO and Virgo, mostly LIGO and Virgo, because Kagura, I will talk about Kagura in a bit later, but the operations only last for 2 weeks, so we don't expect, we didn't really detect any significant event. But anyway, in this diagram, okay, you can see many dots here, okay, so the size of the dot represent the mass of the black holes, okay, and then you see 2 in the upper panel, which is the two black holes or neutron star, basically the two objects, okay? And after the two things merge together, then form just one single thing here. So the larger one, for example, this one is very, very large, which means that it's a more massive black hole. So it's this diagram just to show you the number of confirmed gravitational wave events so far. So altogether, we have 90 event, okay, confirmed event. Okay, but if you count this diagram, actually there are 91. Okay, there's one event which is, it seems that I think it's just it was detected in the O3A. Okay, but when we analyze the data, it seems that the significance is not that good. Okay, so it's kind of a marginal event. But in any case, the collaboration just include that event into this diagram. So altogether in this diagram we have 91. But in general, when we mention about the number of confirmed cases, there's a 90 confirmed gravitational wave event. Okay, so this is another very interesting diagram, okay, to show you the distributions of mass of the two objects and also the final objects after the merge. So what it is showing in this diagram is like this. All the blue circle here are the black hole system discovered by gravitational wave. Okay, and then the vertical axis here is just to show you the solar mass. So, so you can see that, for example, you can see, take this one, okay, so we have an object, a black hole, something like 6-7 solar mass, combined with something with maybe 11 solar mass, and then to form an object which is about maybe 17 solar mass object, okay, so then we have two objects, and then we become one more massive object. So all the blue circles are the gravitational wave event. All others, for example, the red points here are the black hole system discovered by using other electromagnetic wave observations, okay, by astronomers. Okay, so for example, by using the X-ray observations and also follow that up with optical observations, we can constrain the mass of the black holes. Okay, so we can see that the black holes discovered by the electromagnetic wave observations, the distribution, roughly speaking, from around 3 solar mass to roughly 20 solar mass. Okay. And then here there's also some circle with yellow. Yellow is just the neutron star systems. Okay. So the neutron star system, roughly speaking, is about the maximum is roughly speaking about 2 solar mass here. Okay. So in this diagram, you can also see that some of the gravitational wave events also related to neutron stars. So for example, these orange points here are neutron star systems. Okay, so the neutron star can also merge. For example, you can see that for example, this one, 2 neutron stars merge, and they become for a massive object. So if you look at it very carefully, okay, these objects is with orange, half blue, which means that we don't know exactly what it is. So if you look at this, the mass is about 3 solar mass. Okay, so I will talk about this later as well. So this is what we call the mass gap. Okay, so there are 2 mass gaps. One mass gap is in the higher mass objects. The other mass gap is basically between the neutron star and black holes. Okay, so there's no very well-defined cut to classifying objects, or on the other. In other words, there's no clear cut for the lowest mass black holes or the highest mass neutron stars. So that's why we don't know exactly the nature of these objects. Okay. Now, this diagram is interesting because it shows you some visualizations. Okay, what we have so far. So one obvious thing from gravitational wave event is that it seems that gravitational wave event can pick up more massive black holes. So if you look at the red objects, the maximum is about 20 solar mass, okay, which is from electromagnetic observations. For gravitational wave, we can easily observe something up to 50 solar mass or even over 100 solar mass after the merge. Okay, so it seems that we can pick up massive objects easily. But of course, this is kind of a a bias in terms of the observation, because more massive objects, they in general can produce a stronger gravitational wave. But at least there's one strong message is that massive black holes exist in the universe. Okay, so we can observe something up to 50 solar mass before the merge, and even more massive objects after the merge, over 100 solar mass. Now, here I just summarized several key discoveries from astrophysics point of view. Okay, of course there are, if you look at all the LIGO, Virgo paper, there are actually many papers. Okay, and then there are many major discoveries as well. But here I just summarize several things that I think is really interesting. Okay, so first of all, okay, apart from merging black holes, okay, so the first event is emerging black holes. Okay, and then we also discover merging neutron stars. So two neutron stars can merge together. And not only that, okay, we can also discover the electromagnetic counterpart associated to one of the events. So this is very important that I will come back to this issue in a moment. And then we can also observe, okay, neutron star and black hole, they can merge together. Okay, so this is just different combinations. Okay, so from gravitational wave observations, we now know that there is something merged like this, neutron star and black holes. And then from the previous diagram, okay, the diamond diagram, okay, we know that, okay, there's an intermediate mass black holes. So if you still remember, the maximum mass of a black hole, we are talking about several tens of solar mass. So roughly speaking, around this line. Okay, so for anything above hundreds, we can classify them as intermediate mass black holes. Okay, so they are something that maybe end up a very important types of black hole to form supermassive black holes in the futures. So we now confirm that we have the intermediate mass black holes by merging two black holes. And also we discover gravitational wave of objects in the mass gap. Okay, so this is also very important because it's also related, for example, can we have a maximum mass of the neutron stars? Okay, so this is one very interesting question no matter in physics or in astrophysics. Okay, so first let's just look at the first event associated with emerging neutron stars. So here just a artist's impressions of that two neutron stars merge together. Okay, and then when two objects merge together, they are likely to emit some light. Okay, this light can be in optical, in infrared, radio, and of course also in high energy as well. And one of the popular model for merging neutron star, okay, when the two neutron stars merge together, it will produce something called gamma ray burst. It will emit a very strong gamma ray burst, or gamma rays emissions, and the durations is very short, only lasts for just a couple of seconds. Okay, but at that moment you will see a strong gamma ray flash in the sky, and then if you have detectors, okay, to detect gamma ray flash, then you can find the gamma ray burst. The important features of this event, okay, this 170817, okay, of course discovered in 2017. Okay, this gravitational wave event, we know that it is associated with a short gamma ray burst. Okay, so in gamma ray burst we usually classify short and long, just because of the durations. And also the formations of short and long gamma ray bursts are different. Okay, short gamma ray bursts usually associated with merging neutron stars. Okay, so in this event, we also discover, of course, strong gamma ray, and also basically all emissions from entire electromagnetic spectrums. Okay, so this is a very important thing. I will show you a graph in a moment as well. And then the other event discovered in 03, okay, is a event with a very massive neutron star. This event in 1904-25, the combined mass of the neutrons are 3.4 solar mass. Okay, so no one knows exactly the nature of these objects. It could be black holes, but we cannot really totally rule out that it may be a supermassive neutron star. Okay, so this is something that some physicists can work on how to produce such a massive neutron stars. Okay, so this is just a diagram to show you that this very famous event. So when we have the LIGO detectors, and then we have also a gamma ray telescopes. So from the LIGO detectors, we see this very beautiful signal from the in the time frequency diagram. So we see a strong signal here, and then this is the gamma ray light curve. So basically, at the same directions, almost at the same time, there's a small delay for about 2 seconds. Okay, there's a small burst, okay, in the gamma ray detectors. So, and the nice thing is that for gamma ray burst observations, we are quite mature, because this research lasts for over 25 years. Okay, so whenever there's a gamma ray burst in the sky, many telescopes will just look at the same direction. Hopefully, can find out the physical natures about this gamma ray burst event. So, so like in this event as well, many astronomers just follow up this gamma ray burst, okay, and then to hopefully we can find out something interesting associated with the gamma ray burst. It turns out that after combining all the observations, okay, we can now know that this gamma ray burst is also associated with the gravitational wave event. Okay, and this diagram shows a very complicated. It looks very complicated, but it's just to show you basically all the observations related to this gamma ray burst event, this gamma ray burst and gravitational wave event. So in addition to the gravitational wave signal and also the gamma ray burst signals, basically you can see the source across the electromagnetic spectrums. We have the optical, infrared, X-ray, okay, and also in radio as well. So even the emissions now, if you look at it with X-ray telescope, we can still see the emissions from this event. Okay, so basically it's the afterglow, the tail of the emissions. Okay, so we can learn a lot about. So basically we can pinpoint the directions. So for example, in this picture, it shows you the first discovery pictures. Okay, in the optical light. So this is a galaxy. So you can see a point next to it, a new star here. So this is an image taken about 20 days before the detections. So there's nothing, obviously nothing in at this positions. And suddenly there's a bright object, just an optical star. They are just optical objects. And then we can, by discovering these objects, we can follow them up with other observatories, and also for example take the spectrums, then we can measure the redshift, and we can get all those informations. So we are quite sure the natures of these objects. So this is just a light curve of these objects. So we can see they suddenly become very, very bright, and then just faint slowly over time. So this is very important, but this is also the only one gravitational wave event that has electromagnetic counterpart. Okay. Hopefully in the 04, we expect that at least one more event, okay, by using all the detectors, okay, and also improve sensitivity. Now, the other important discovery about the gravitational wave observation is the formation of intermediate mass black holes. So if you still remember this diamond diagram, okay, we know that there are several objects here. They are over 100 solar mass. Okay, and the most massive one we have is this object. Okay, and the combined mass is about 142 solar mass. And also the two black holes, actually they are also quite massive, more massive than all the black holes discovered in electromagnetic spectrums. Okay, so this is a very important. It has a very important implications for astrophysics. So altogether we have three, okay, and there's three confirmed intermediate mass black holes okay, according to gravitational wave observations. And of course, we have the merger of neutron star and black holes. Okay, so this is also very interesting. So they are mostly objects like here combined with a black holes, and then they form a slightly more massive black holes. Okay, and one of them are interesting for many physicists as well, because it has an extreme mass ratios. So the black hole is 31 solar mass, the other object is 1.2 solar mass neutron star. Okay, so of course we can study, for example, the general activities by using this type of objects. Okay, so it's also show you that in gravitational wave, okay, basically we can discover some many more interesting or assorted objects, okay, in the universe as well. Okay. So from gravitational wave observations, as I mentioned before, okay, we discover objects in what we call the mass gap, which is basically there are two mass gaps. One is between the black holes and neutron star, which is about 3 to 5 solar mass. Okay. So, for example, depending on the natures of neutron star, okay, some people believe that a neutron star can be more massive. Okay. And then also another question is that whether there's a minimum mass for black holes. So there's always a mass gap. At least from electromagnetic observations, it seems that there's a gap between in these regions. But in gravitational wave observations, they clearly show that there's something in between. It's very obvious there's something in between. So they are the mass gap objects. Okay, of course, we always want to know the natures. And then the other mass gap is in the upper bound, which is about near 50 solar mass, 50, 60 solar mass. Okay. So this is due to the fact that when an object forms a black hole, it needs to go through supernova explosions. Okay. And in supernova explosions, there's a process called the pair instability that can allow the collapse of the star all the way without going through a black hole. Okay. So in this case, from theoretical simulations, okay, they predict that there's a gap around 50, 60 solar mass. Okay. So and then just basically there's no black holes above this range. Okay. And obviously from the gravitational wave observation, you can see the sub-object. For example, this one is about 50 solar mass. Okay. Of course, there's an uncertainty here, so that object may be also something interesting. Okay, if you're interested in the objects in the mass gap. Okay, so these are some very important message, okay, from previous observations. Now, if you want to study the natures of the objects, for example, if you find an object in the mass gap, a gravitational wave source, if you just look at the gravitational wave, it cannot really tell you a lot more, okay, apart from for example, the mass of the objects, if you look at the spin of the objects, the inclination angle, the distance to the objects. But we don't know, for example, the environment. So what kind of environment can trigger this kind of black holes, okay, or how it's evolved. Okay, so we cannot tell from gravitational wave event. So we need to look at. So that is why it is important that we should find out the electromagnetic counterpart. For example, in optical observation, we look at a star. Okay, and then from the stars, we see the light variation of the stars, and then we realize that this star may be, for example, a supernova, okay, or a very weird supernova. Okay, then we can start to study the astrophysics. Okay, so the electromagnetic counterpart is very important. However, in gravitational wave detectors, even in the best scenario now, we have 3 detectors, 2 LIGO detectors and 1 Virgo detectors. Even in the best scenario, which is this one, 170817, this is the localization uncertainties in the sky. Okay, so for this case, we are very lucky because for this source, it's also quite nearby. So the signal is quite strong, so that the localization is quite good. Okay, but for the rest of the event, you can see that basically it's covering a large region of skies. So this is the Milky Way. Okay, If there's some of you, if you come from astronomy club, you may know that this is the Milky Way is a very large region in the sky. Okay, and if your uncertainty region is that big, it's almost impossible for you to identify the counterpart because there are just so many stars. Just so many stars. So this is also the reason why, so far, only one event, only this event, will have the electromagnetic counterpart. But for the others, it's extremely difficult. Extremely difficult. It's just too big. You have to spend a lot of observing time, telescope time, okay, to survey the sky and look at the transient. Okay. So how can we improve this? Obviously, we can just put one more detectors. Okay, so this graph is show you that the improvement of the localizations. Okay, so this is just to show you that, for example, if there are just 3 detectors, 2 LIGO detectors and 1 Virgo detectors. Okay, so in the best case scenario, is this curve. So, for example, 90% of the source, the localization area may be about 50 to 60 degrees, square degree in the sky. It's a huge region. So it's really not easy to cut out the transients. But by adding one more detectors, okay, the C here is, means Kagra. So now we have 4 detectors on the ground. And then if we look at this curve, 90% of the source, the uncertainty of the localization is about within 10 square degree, which is much more reasonable regions. Okay? Especially nowadays, we have some detectors, optical camera, they have a very wide field of view, a very wide angle telescope, so that we can observe the regions and to pick up all the potential sources. So this is the reason why we want to have more detectors on the ground. So this is a diagram to show you, a map to show you the locations of all those detectors. So we already introduced the LIGO. So we have the 2 detectors, one in Hanford, the other in Livingston. And then we have the Virgo in Italy. So in O2 and O3, basically these 3 detectors work together. Okay. Geo600 is in Germany, but this detector is mostly for testing, okay, for calibrations. So the sensitivity is not that good compared with the 3 detectors. So there is actually, we don't expect to see anything from this detector anyway. Okay. And then in a moment I will talk about Kagra, which is in Japan. Okay. So in 04, which will happen by the end of this year, then we will have 4 detectors, 2 LIGO, Virgo, and Kagra will observe the sky together. So that is good because if we can observe a gravitational event with 4 detectors, the localization will be significantly improved. In the futures, I think the current schedule may be 2025. There's also something called the LIGO India. So basically just copy the entire LIGO detector and put it in India. So by that time, we will have a much better localization as well. So this is the current map, okay, of the detectors. So Kagra.
How about distance?
Yeah.
Distance accuracy.
You mean distance to the source?
To the source, yeah,
to the source. It depends on the, for example, the how strong of the gravitational wave signal. Okay.
Yeah, of course.
Yeah.
If that can be addressed, the natural question is what has been the observed distance distribution?
Okay, the distance distributions. I'm sure there's some paper that describe the distance distributions, but at the moment I don't have the number in mind. Okay, but sure. Well, the one obvious thing is that the distance we will, because of the improvement of the sensitivity, okay, we will see more distant objects, distant wave objects. So Kagra. The main difference of Kagra compared with the other 3 detectors, okay, the 2 LIGO and 1 Virgo, is that the entire detectors, the Michelson experiment, the L-shaped thing, is built underground. So this is a very famous super K detectors for neutrinos. Okay, probably many of you know about that. Okay, and then so we build the detector next to Super K. So it's basically in the west coast of Japan. Okay, and then so this is one thing. By building the detector inside a tunnel underground, okay, we can minimize the seismic noise. So basically, so this will further enhance part of the sensitivity. Okay, and then the other groundbreaking thing for Kagura is that for the rest of the detector, for example, LIGO and Virgo, they work in room temperatures. Okay, the experiment work in room temperatures. Okay, but for Kagura, okay, we have a cryogenic system to cool down the mirror, to cool down the system into a very low temperatures in order to reduce the noise. Okay, so this will also enhance the sensitivity, okay, in the detections. Okay, and the arm length is about 3 kilometers, so very similar to Virgo. Okay, so this is just the picture inside the tunnel. So the entire thing is just built inside a tunnel. Okay, so when you visit Kagura, you need to walk inside in a tunnel for about 15-20 minutes from the main road and here, and then you can just basically work in here. But the operation center, so there's also, I think there's the pictures. The operating center here, okay, is about a few kilometers from the main site. So the observer, okay, or the staff didn't really stay in the Kagura site. This is just the entrance of the tunnel. Okay, so this is just the split mirror. So here it's just basically this mirror. It's a scale up version here in Kagura. So Kagura, if you Kagura basically is just a pronunciations, okay, very similar to a Japanese kanji, sanno, which is basically means that a dance in front of God. Okay, if you know this cartoon, okay, so one of the most powerful strike of the main character is the Hinokami Kagura. So this Kagura is just the sound very similar to Kagura. Okay, so they use this as the name for the instruments. So this is sanno. Okay. So this the PI, the PI of this project is Professor Kajita. Okay, so he actually awarded the Nobel Prize in 2015. Okay, but it's not for gravitational wave, but for his contribution in neutrinos. Okay, here is just a lectures, a seminars, a workshop that we organized in 2015, and this is actually very interesting because we organized this. Some of the Taiwanese scientists invite him, Professor Kajita, come to Taiwan by the end of 2015 to organize a workshops. Okay, and all of a sudden, okay, he got the Nobel Prize in October. Okay, so we are very, very aware about that. He won't come, okay, because he will be very super busy. But at the end, he kept the promise. So even only stay in Taiwan for only a few days. Okay, he and also his team come to Taiwan, okay, to help us to organize a workshop. And one of the objectives is that actually he come to Taiwan frequently, and hope to establish collaboration between Taiwan and Japan, especially on this Kagura project. Okay, and I'm lucky that I take the lead of the effort, okay, to group some Taiwanese scientists to work on the Kagura team as well. And now, basically, Taiwan is the largest international partner of Kagura. So apart from all the Japanese scientists, the second largest group is from Taiwan. Okay, so as I mentioned to you before, okay, Kagura will begin to join the observations from 2022 December. So we are looking forward to the observations, and hopefully there's no more delay. and then we will observe together. And we will expect to see some, hopefully there's some interesting results from that as well. Now in the next 10 minutes or so, I will introduce some of the work that we have done in Taiwan, okay, under this Kagwa collaborations. So at the moment, in Taiwan, we have several institutes that are members of Kagwa. So of course, apart from NTSU, we have your labor, NTNU, my labor, NYCU, and also NCU, NCKU, TKU, Academic Syndicate Institute of Physics, and also the National Center for High Performance Computing. Okay, so currently they are the members of Kagwa. And what you see here, you can see some red color thing here. So NTSU, NCU, and the IOP, they are also LIGO member. Okay, so in terms of the formality, there's not much different for being a LIGO or Kagwa member in terms of data analysis. If you work on the data only, basically more or less the same, because whenever you are the member of Kagwa, you can access all the data from LIGO and Virgo, and we are under this what we call the LVK collaborations. Okay. The major difference is that if you want to work on instrumentations for particular detectors, okay, you need to join that collaborations. Okay. So for example, for NTSU, we are also the most famous thing for the LIGO is the mirror coating. So it's done by in NTSU, and also NTSU, the other team, the Kagwa team, is also working on the squeezings that I will show you in a moment. Okay, so depending on the instrumentations, okay, you need to join a specific collaborations. But in terms of data analysis, there's no difference. Okay, so we can, as long as you are a member of Kagwa, you can also join almost any activities related to data analysis, related to LIGO and Virgo as well. So we basically have joint meetings every day, okay, depending on which group you are, okay, and also all the time zone. So, for example, even for myself, I have meeting from yesterday, okay, all the way from the morning to today morning. Okay, I have different scheduled meetings related to the collaborations. Now, for the Kagwa, the first observations was done in April, for 2 weeks in April in 2020. So, the reason why there's only 2 weeks is that because of COVID-19. Okay, it's also unfortunate that by the time we start the observations, the Kagwa observations, LIGO and Virgo were shut down because of COVID-19. So in principle, LIGO and Virgo should observe for 1 more month, but because of the COVID-19, they shut down 1 month earlier, so that we just missed the opportunity to observe with LIGO and Virgo. So at that time, during these 2 weeks, okay, we just can observe with GEO-600, but because the sensitivity of GEO-600 is also not very great, so we didn't detect any significant event. But anyway, I think the first paper coming from Kagwa, from real observation from Kagwa, will come out very soon. Okay, so here, because today I will just focusing on the data analysis here, just to show you some instrumentation thing. For example, this is the in NTSU, we have the work on the LIGO coating. Okay, probably you see some of the press release when there's a first detections of gravitational wave event. Okay, we work on the coating on the surface of the mirror to increase the sensitivities. At the same time, there's another team in Kagwa, okay, led by Li Weiguang. So we work on the squeezings. So to reduce the quantum noise of the detectors. So this is basically, so here the squeezing is not implemented in 04 yet for Kagwa. Okay. And we are now building the experiment, and hopefully we will integrate the system for 05. Okay, so this will be for next cycle. I think for Virgo, they will start the squeezing observations from 04, so they are a little bit ahead of us. But anyway, we are now leading the effort for squeezing in Kagwa at NTSU. And of course, for example, for NCU, they are leading for the calibration system, okay, for LIGO and also Taiwan. Academic Syndicate, Institute of Physics, they provide a high-power laser system for Taiwan for 05 as well. Okay, so there are a lot of instrumentation activity in Taiwan as well. So hopefully, in the future, some of the curriculum, you can invite them to talk about the instrumentation thing. It's also quite interesting. So for data analysis, there's so many different types of data analysis. So here I just focus on something that Taiwan work on. So first of all, we have something called the surface data analysis. The surface means that we have some well-established standard data analysis pipeline. But because there's so many signals, okay, so we need to divide the work into many different teams. So for example, at NTSU, okay, we help to, for example, search for gamma ray burst, okay, from the gravitational wave signals. And more recently, we also start to search for the fast radio burst, FRB, okay. And we are also helping, in 04, we will also help to search for the core collapse supernova. But it is, I have to say that if we are really, really lucky, that we have a very nearby supernovas. Okay. And also, we have to work on the offline parameter estimations. Now, why we call this offline? Okay, because for parameter estimations, usually when we detect a gravitational wave event, we have some very quick analysis to tell you, for example, the mass of the objects, the localizations, the positions of the objects, but they are very rough. So usually after the observing one, we will establish a team to work on every single signal, okay, and then to spend a lot of computation power to work out the exact parameters, okay. So it takes a lot of human resources and also computation power, okay. So we also help about this for these parameter estimations. At NTSU, we also developed the waveform for core collapse supernova. Okay. The waveform is important in gravitational wave astrophysics because one of the major data analysis technique we have is to compare the waveform with the actual data. So you can imagine that, for example, for the binary black holes, so depending on the combination of different physical parameters, you can generate the waveform from numerical relativities. So we are talking about, at the moment, in the database, we have over 1 million templates or million combinations of different physical parameters. And then we just compare the signal with this million set of database. And then if something match with the database, then we can say that, okay, we find a candidate. Okay, this is what we call the match filter method. Okay, to compare the theoretical calculations with the real data. Okay, but it's quite time consuming. Similarly, we can also do the same thing for a supernova event. When a supernova happens, it also can emit gravitational wave. So we can compare the waveform of the gravitational wave with the real data. But unlike merging neutron star, merging black holes, you can do it with numerical relativity relatively easy. Okay, you can easily generate many templates. Okay, but for supernova explosions, it is very expensive in terms of computations. Okay, it can easily take a month to generate the waveform. So it's a very time-consuming thing, and also it involves a lot of complicated physics, nuclear physics. But anyway, we are working on the waveform generations, and of course in the future, to speed up things, of course we can also implement machine learning technique in data analysis, okay, including the generate waveform as well. So at the moment, there are also some machine learning activities in Taiwan for gravitational wave research. We work on the parameter estimation with machine learning, like in Academic Syndicate and NTNU, gravitational wave detections, okay, NTSU and CKU, and also in NYCU, they also use a machine learning technique to reduce noise. So there are some activities around Taiwan for the data analysis. So here is the, we also developed some new method when you detect gravitational wave. Okay. So this, for example, this is a method that we are now working on, is the using what we call the Hilbert-Horn transform, okay, to detect the signal. So here on the right hand side, you can actually see the diagram, okay, similar to what you see before. You see the signal in the time frequency diagram. But if we look at, so for example, in the middle of the in the diagram, okay, this is basically from the usual Fourier transform technique. But at the bottom two panels, okay, we are using the Hilbert-Horn transform to evaluate the signal. It seems that we can achieve a little bit higher resolutions for that. On the left-hand side is a diagram to show you that there's a supernova explosions. You can also use this Hilbert-Horn transform to detect some interesting signal, okay, from the data. So this is something that worked by my colleague. Okay. So he generated the gravitational waveform. Okay, so basically his research interest is on supernova. So he produced many very, very beautiful simulations. So on the right hand side, just see the computer simulation using the high performance facility, national facility in Taiwan, okay, to generate this type of very beautiful simulation for a supernova event. Okay, and then he can generate the waveform and then compare with the data. And of course, this kind of simulation is very expensive in terms of computation. So he also worked with my student as well to look at using the machine learning method to generate the waveform and do parameter estimation as well. Okay, so this is just some of the rough result from his simulations. But here we just show you the just using the typical Fourier transform method to look at the time frequency diagram. The resolution is not great, so that's why we are now trying to do it with the Hilbert-Horn transform to increase the resolutions, and hopefully we can discover some new thing in the data. Here is actually a student from Professor Wu. Okay, so he and his student is now my postdoc. Okay, work on the machine learning technique called the Bayesian neural network method for gravitational wave detections. And the one very important thing about this technique is that we can really assign an uncertainty of a possible event. Okay, and also this is very important for an alert. So we can tell people how likely of this supernova of this gravitational wave event is real or not. So this is very important. And of course, they also have some implementation for forecasting. Okay. We are now improving the algorithm. Hopefully we can do this forecasting. It's very important because when you can forecast even 1 or 2 seconds before the event, if you can signal that is a possible gravitational wave event, then we can organize observations on the ground to look at the possible counterpart. Okay, so this is something that we want to achieve in the futures. And now we are talking about to redesign the code for noise hunting. What we call the noise hunting is that in the gravitational wave observation, there are lots of many different types of noise. If you're interested, you can go to the website called Gravity Spy. Then this is actually a citizen science project. Then you can see many different types of noise in the gravitational wave observations. Okay, so the reason behind that is that instead of detecting the signal, we try to detect the noise. And then we know if it is a noise, then we can just subtract from the signals, and then we can have a cleaner signal for source detections. So we just we are hoping that we can use this method to look for any potential noise inside the signal, and hopefully to improve the sensitivity in the futures. At TKU, also people working on the gravitational wave background, which is, I'm not going through the details, but the gravitational wave background is related to the early universe. Okay, it can also related to in the universe. There may be some signal, a combination of many merger events in the universe, okay, and this just as a background. Okay, so we can use gravitational wave, the detection method, to see if we can produce the gravitational wave background map. It's just very similar to the cosmic microwave background. Okay, hopefully we can understand the early universe by using this observation as well. So if you're interested in electromagnetic wave, you can throw up every single alert from gravitational wave detectors. Okay, so this is something that you can, if you're interested, you can work on the download the software. Okay, so there's two software that allow you to receive the alert. Okay, whenever there's a signal coming from. So basically, you can see on the upper left, this is the roughly the schedule. Basically, we can send you the alert within 1 minute of the detections. This detection is a potential candidate, okay, within 1 minute, okay, so that you can just point your telescope and to do the follow-up. But it's quite common that the alert turns out to be a false alarm. Okay, so if you can wait, usually after 1 or 2 hours, they may have another alert to show you that to show you more information about the alert. For example, some rough parameter estimations, or even if maybe the alert is a false alarm, they can retrieve this. Okay, and then for other more details work, we can just work on it well after the event. So, but anyway, if you're interested in the electromagnetic follow-up, you can just download these two apps. So we can learn a lot of things by the multi-messenger, okay, which means to combine the electromagnetic wave observations in addition to the gravitational wave. I'm not going through all the details, but by combining the two messengers, okay, we can learn a lot, okay, from this event. There are many ways to look at the data, because so one obvious way is that if there's a gravitational wave, then you can just trigger the electromagnetic observations. But we can also do it another way around. So this is something that we are also working on now. So even the data are now basically a public. It's now open to public. You can download the data by yourself if you know how to do the data analysis. Okay. So suppose you discover a new supernova, you can just go back to the gravitational wave data and then to see if you have something interesting. So depending on your applications, you can work on the data again as well. My students are also working on the, for example, to study the more astrophysics part from the from gravitational wave event. For example, this famous 1709-17, the emerging neutron stars. Okay, we are also making use the information from the electromagnetic wave to constrain, for example, the jet structures, okay, or the geometry of the systems. Okay, so we compare with different models, and then although currently the data is still not good enough to really to tell exactly which model is true, but hopefully in the future we can, with more sources detected, we can have a much better understanding. So I will just summarize these pictures for 04 and then end the lectures. So what we expect in 04, which will happen in December this year, hopefully we will find more electromagnetic counterpart. Currently we only have one. So the other question is that can we observe the electromagnetic signal from black hole system? So this is really a very debatable questions, whether black hole system can emit light, okay, during the merge, okay, or neutron star black hole system. Okay, so this will be very interesting. The physical natures of sources in mass gap, okay, so as I mentioned to you before, it could be a very massive neutron stars or very low mass black holes, okay, and also the maximum mass black hole neutron star. Black hole spin, for the moment we only have a very broad estimate. We know that it's spin, but how fast it is, we don't really have a good constraint. Hopefully we will detect some shorter binary, like magnetar, FLB, or maybe other interesting objects. The other thing that I didn't cover today is the continuous gravitational wave, is that when the neutron star spin, okay, so suppose neutron star is not really symmetric, or there's a mountain on a neutron star, okay, it will produce continuous gravitational wave. Okay, so at the moment we didn't have any detection yet. Hopefully in O4 we can solve this problem. Gravitational wave background, once again, is very important for cosmology. If we're really lucky, if there's a very nearby core collapse supernova, okay, then it will be a very big event. Okay, so I will stop here and thank you so much. Thank you.
Yeah, thank you for quoting mine and my students' paper. So we know we NTU contribute also a little bit to the collaboration. So now we'll open the floor for questions. Any questions for the speaker? Yes, please.
About the localization of the gravitational
Can you speak louder?
It's about the localization of the gravitational wave on the sky. You mentioned that only one gravitational wave can have its electromagnetic counterpart, and because its signal is stronger. Why is the intensity has anything to do with the localization of the gravitational wave?
Okay, so if we have a brighter signals, okay, so we have a better signal to noise ratios, so we can improve the localizations. Okay, so this is one thing. The other thing is that for that particular source, there are 3 detectors, so we can really we can constrain the localization even further. Okay, so if something is very faint, so you will expect uncertainty will be very large. So it is really related to the signal to noise ratios, okay, and also how many detectors that you are observing when the gravitational wave begins.
Okay, yes, ready.
Thank you for a fascinating talk. You mentioned FRBs twice or more even. Is that meant to connect to a specific experiment?
Yes, we have MOU with several FRB collaborations. So whenever there's a trigger, then we know where to search for.
Yeah, I think you two should talk.
Since Taiwan is building an initiative to find nearby FRB, so 100 megaparsec volume, which might be very interesting for cross-correlating.
Yeah, sure. If you are interested, then of course we can talk about that.
He's working on that.
Yeah, I know.
Thank you.
Okay, great. Any more questions? Yes.
About the GW background, what is the requirement on sensitivity and the frequency range you need in order to observe them?
Well, the frequency range is basically fixed by the instrumentations. So we cannot really change the frequency range. The sensitivity, I don't have a number in my mind because I'm not really working on the gravitational wave background. But at least at the moment we haven't had any confirmed detections for that.
So any rumor, comments, or news from about Lisa?
About LISA, oh yes, I should also mention LISA. Well, of course, LISA is an approved missions by ESA. Okay, so we are quite certain that we are aiming for the launch at 2035, I think.
2035.
Yeah, 2035. And Taiwan is an associate member of ESA. And I'm currently the convener in Taiwan. So if you want to join LISA, you can just talk to me.
It's been deferred for a long time. Deferred. Okay.
Um,
With a different stakeholders. Yeah.
Yes, but at least now we have a secure funding from ESA, so I think it should
Yes,
be
better.
all right.
Yeah.
Yeah.
Because in old days there was this funding disaster.
Yeah.
Any more questions?
Sorry, maybe I
Sure.
It's also related to the localization. So that source also have a detection for Fermi, right? And I would imagine that Fermi also helped the localization. And another thing is that if my understanding is correct, Fermi actually only can monitor a fraction of the sky. So the reason that the gravitational wave and the gamma ray can be detected simultaneously, it's sort of by chance, right?
Oh yes, absolutely. And of course, 17017 is lucky that we also have the Fermi observation from gamma ray. So it helps for the localizations. But basically, for every single gravitational wave event, some surveying telescope, like for example ZTF, we basically monitor the regions as quick as possible for a large region of sky. But at the moment, it's extremely difficult in that case. Yeah.
Okay, thank you.
Right. More questions? Yes.
Thank you for the talk. And during the talk, you mentioned that for co-collapse supernova, you do some machine learning because for the simulation you need maybe 1 month or so to make some simulation. And I'm curious how you do this machine learning and how to reduce the time or to
Yes, at the moment my student is working on a machine learning method called the conditional variational autoencoder, CVAE. So this kind of technique can be, as long as you input, well, we need to train the machine with some known waveform. So this part, my colleague can produce some of the waveform. And the powerful thing from this machine learning technique is that after we train the network, we can just input just arbitrary parameters, and then the machine can generate a new waveform. Yeah, so that will really speed up the simulation result.
More questions? Yeah, George.
I want to go all the way back. When you said by 0405 there will be several hundred megaparsec sensitivity, what does that really mean?
Okay, so
I mean, this is related to my distance question. Of course, it depends on the intensity, but yeah, okay.
this is assumed that is a two neutron stars they merge together. So it just depends to calculate the distance, how far we can observe if two neutron stars merge together.
So it's based on neutron star.
Based on neutron star. If you are talking about merging black holes, I think it's at least a factor of few, okay, more. So probably more close to gigaparsec.
But still, I don't get fully that picture. 300 megaparsec, in principle, you are seeing beyond Andromeda. So I like to see that distance correlation. Are we going to be able to see mergers from Magellanic Cloud, for instance?
Magellanic Cloud, of course, because it's very nearby. So if something happened in Magellanic Cloud, that it will be great.
But it comes back, of course, to the distance sensitivity, or your error in distance.
But Magellanic Cloud is...
Anyway, I guess my question is in part saying that suppose some very energetic gravitational wave event occurs in the Andromeda. When are we going to see that on this time scale?
Well, for Andromeda is about 800 kiloparsec. So basically, if something happens, we can actually observe in O1.
So it's possible. Yeah.
Yes. Yeah,
Okay.
Yeah.
Good.
Yeah.
Okay, more questions? If not, then let's thank the speaker again. Thanks, Alpha.
Thank you so much.
这物理所倒是有做在中研院，但是
有啊，里面是健康，有些开吧，其他没有，不好意思吧。所以你们是到6点半，就跟他们一样。陈一峰呢？陈一峰没来。应该有。我刚刚那个回应就是，我要回应就是。你讲在那边。他如果到时候在这里，所以你怎么讲话就是应该要在嘴巴或是那个夹里头，其实。像我们这样一般应该加油吗？因为这个跟教具有关系，因为是原来是教具有关的应该是跟那个，但是它不会做这个，但是这个设备什么之类的，它都会找。我们有2个。然后去年我上天去的时候，在高速突然就学生在那你说在哪里？对对对，这样演的话，这声音就对，然后他们就不想，不懂，学生不懂。但是我记得我们那时候让他修个衣服，我再看看，真不好意思。照理说应该是很多支的。Two reasons that we have not. 所以我们也是在这方面的技能上面的我们staff也缺乏专业气球跟什么飞机，终于知道。不过我说我们在研究上面前标。交帮你准备的。哦，陈信宇啊，陈信宇，对啊，因为他不只是我导师，他拿我知道，听说在高阶科展的时候出时代了。他现在就是做这个，他现在做蛮多的，他跟上。他是不是现在上那个美丽那个老师叫什么？
啊？哦，不是几乎很量会好像可以用在更大量。哦，是。就决定我骑进去问这样，所以你细半对，我就所以你没有商量力啊。我让我分享。哎，所以你有做发现？我没有，我那个就只是看。不在这里面，大概在别的地方。哎呦，呛哦！不修量力要更糟糕吧？我就修过了，因为他拿到哎，穿插就是第一面还是对啊，所以他怎么可能？对啊，而且他如果继续跑，刚上层，所以我不知道很但进攻也是。我可以完全了解，所以我就说那就不用了。他广义相当于大我慢一下，就是。确实，那你怎么不学？我都不学。广义相对的，还是你有？就撞课啊。然后撞了怎么了？撞专考。来啦，广义相对是礼拜3，不是礼拜2。对啊，7、8，他撞7吗？他撞7。对啊，看，只要4本就可以保证拿5技，他拿2本。干你兄屁哦！都误技。那你还有说什么？啊，讲得很累，我